Numbers 89 and 92 are both Henry's law problems. And what Henry's law says is basically that the solubility of a gas is directly proportional to the partial pressure of that gas. We can explain that using this nifty little equation here. S1 over P1 equals S2 over P2. What the S's represent are solubilities, right? They can be in any of the units we use for concentration, grams per liter, moles per liter, percent by mass, so on and so forth. P's represent the partial pressure of the gas, right? That's going to be in some sort of pressure units, atmospheres, kilopascals, torricellis, millimeters mercury, and so on. 1's represent our initial conditions, 2's represent our final conditions. So in number 89, we're said that at a pressure of 1.5 atmospheres, the solubility of a gas is 0.54 grams per liter. We want to know what happens when the pressure is doubled. So we can take that 0.54 grams per liter and 1.5 atmospheres being our initial conditions. If we double the pressure, that gives us a total pressure of 3.0 atmospheres. So on the left side, we have 0.54 grams per liter divided by 1.5 atmospheres. On the right side, what we don't know is the solubility, the S2, but we do know the pressure, 3.0 atmospheres. Solving for this S2 gives us 1.08 grams per liter. Number 92 is a similar problem. However, in 92, instead of solving for a solubility, we're solving for a pressure. So 92 says that the solubility of a gas at 37 kilopascals is 1.80 grams per liter. We want to know at what pressure the solubility will reach 9.0 grams per liter. Okay, our initial conditions are our 1.0 grams per liter and our 37.0 kilopascals. We don't know what our final pressure is, but we know that our final solubility is 9 grams per liter. We can set up our equation like this. Solving for P2 gives us a final pressure of 185 kilopascals. 99 and 102 each involve colligative properties. And what colligative properties are properties that depend on the total amount of solute particles in solution, but not on what kind of solute particles are in solution. And there are 4 colligative properties. There's freezing point depression, there's boiling point elevation, there's vapor pressure lowering, and there's osmotic pressure. Each of these has their own formula that tells us how specifically that property depends on the concentration of solute. The formula for freezing point depression is written up here at the top of number 99. Number 99 is a freezing point depression problem. And what we want to do is we want to calculate the freezing point of a solution of 12.1 grams of naphthalene dissolved in 0.175 grams of benzene. Okay, there's some data for us in table 14.6 to help us solve this problem. First thing we have to do is tease out what's our solvent and what's our solute. This is a little bit different than the problems we dealt with in the past because we had water being our solvent. That's not the case here. Now we have benzene, C6H6, as our solvent. To figure out what the new freezing point is going to be, we're going to have to work with this formula that I've pointed to at the top of 99 here. It says that the change in freezing point, which is delta TF, equals a freezing point depression constant, negative Kf, times the molality of the solution. So what we're going to need to do is we're going to need to calculate the total molality of solute particles. C10H8 naphthalene is an inorganic compound. It's a molecular compound, which means it's a non-electrolyte. That means that each C10H8 that dissolves in solution is just going to produce one particle. So we're not going to need to worry about trying to figure out how many particles we get from C10H8. To figure out the molality, we need to know how many moles of the solute we have. So what we need to do is we need to convert from grams to moles using the molar mass, divide by the molar mass so as to cancel out the grams. Find out that we have 0.0944 moles of naphthalene in our solution. Molality is moles of solute per kilogram of solvent. Okay, we're actually told that we have 0.175 kilograms of our solvent, benzene, C6H6. So that gives us what we need in the denominator of our fraction. Dividing our moles of solute by our kilograms of solvent gives us a molality of 0.539 moles per kilogram. This is something you can then plug into the freezing point depression problem. Okay. If you look back at table 14.6, it tells you that the freezing point depression constant for benzene is 5.12 degrees Celsius per molality. Okay, I have a negative sign in front of this here because our new freezing point, aka the freezing point of our solution, should always be lower than the freezing point of the pure substance. So if we take delta TF to mean freezing point of our solution, minus our pure substance. Keeping that negative sign in there allows the delta TF to always be negative. Okay, if we plug in our constant that we looked up in the table and our molality that we solved for earlier, it gives us a delta TF of negative 2.76 degrees Celsius. That means that our new freezing point is going to be 2.76 degrees Celsius colder than our initial freezing point. That table 14.6 also tells us that the initial freezing point is 5.5 degrees Celsius. Okay, if we plug that in and say that our delta TF equals our TF of our solution minus our new TF, you'll yield that our new freezing point is 2.74 degrees Celsius. Number 102 involves boiling point elevation. And the formula for boiling point elevation looks an awful lot like the one for freezing point depression. Now we've got Kb. What that means is that instead of using the freezing point depression constant, we use the boiling point elevation constant. Instead of delta TF, we have delta Tb. Instead of change in freezing point, we're talking about change in boiling point. Again, this is going to depend on the total molality of solute particles. So number 102, we're told that the boiling point of ethanol, which is C2H5OH, changes from 78.5 degrees Celsius to 85.2 degrees Celsius when an amount of naphthalene is added to 1 kilograms of this solvent. What we want to figure out is how much of the naphthalene gets added here in grams. So the first thing we're going to need to do to solve this problem is tease out what the molality of our solution is. Because if we figure out what the molality of the solution is, we're told how many kilograms of solvent we have, so we can go from molality and use kilograms of solvent to figure out our moles of solute. And once we know our moles of solute, we can use molar mass to get our grams of solute, our grams of C10H8. So to start out here, we've got to figure out what our delta TB is. We take our boiling point of our solution, and we subtract from it the boiling point of our pure substance. That's set to equal this boiling point elevation constant, which for ethanol is 1.22 degrees Celsius per molality, times the molality. Solving for little m here yields a molality of 5.49 moles per kilogram, which means that we have 5.49 moles of naphthalene per kilogram of ethanol. If we start with 1 kilogram of ethanol, we can use this molality to figure out how many moles of C10H8 would have in solution. So if we arrange our molality and use it as a conversion factor, we want to cancel out our kilograms of ethanol. So we want our moles of naphthalene at the top, our kilograms of ethanol at the bottom. Doing that will allow them to cancel out. If we stopped here, what we'd have is our moles of naphthalene. We want to go one step further and then get grams of naphthalene. You go from moles to grams using molar mass. The molar mass of naphthalene is 128.174 grams. We multiply by the molar mass, our moles. Naphthalene cancel out, and you get your final answer, which is 704 grams.